Let's examine what happens when a three-phase transformer bank connected in an ungrounded Wye 13,800 volts/center tap delta 120/240 volts configuration experiences fuse failures. We will consider two scenarios. Firstly, when one primary fuse is blown but the corresponding transformer is intact, and secondly, when the fuse is blown as well as the corresponding transformer. In the first scenario, with one primary fuse blown but the corresponding transformer remaining intact, the remaining two phases will continue to operate, albeit with reduced voltage. The voltage at the secondary will not increase. This is because the ungrounded Wye primary connection is effectively split into two single-phase transformers. The blown fuse on one phase isolates that portion of the transformer from the supply. Consequently, the remaining two transformers continue to operate independently, providing reduced voltage on the secondary side. Now, let's consider the second scenario where both the fuse and the corresponding transformer fail. In this case, the remaining two transformers will no longer be able to provide balanced voltages. This will result in an unbalanced secondary voltage, with one phase experiencing a higher voltage than the others. The voltage on the faulted secondary phase will increase by a factor of the square root of 3, or approximately 1.732. The reason for this voltage increase lies in the loss of the neutral point provided by the ungrounded Wye primary connection. Normally, this neutral point splits the voltage. However, with one transformer failed, the neutral point is lost, and the voltage on the faulted phase shifts by 30 degrees. This shift causes the voltage in the faulted phase to become approximately 1.732 times higher than the normal phase voltage. The impact of this increased voltage on the faulted phase can be significant. It can potentially damage connected equipment that is not designed to withstand such overvoltage conditions. Additionally, the unbalanced voltage can cause problems with motor operation and other sensitive loads, leading to reduced performance or even failure. It is crucial to understand these potential consequences of fuse and transformer failures in ungrounded Wye delta transformer banks to ensure proper protection and prevent equipment damage. Consider a scenario where the normal phase voltage on the secondary side is 120 volts. If one transformer fails, the voltage on the faulted phase would rise to approximately 120 volts multiplied by the square root of 3, which is roughly 208 volts. This significant increase in voltage could easily damage equipment designed to operate at 120 volts. Moreover, the unbalanced voltages could negatively impact the performance of three-phase motors connected to the secondary side. Motors may experience increased heating, reduced efficiency, and potentially premature failure due to the uneven voltage distribution. Sensitive electronic equipment, such as computers and controllers, may also malfunction or be damaged by the voltage imbalance. To mitigate these risks, it is essential to implement appropriate protection measures, such as overvoltage relays and fuses, to detect and isolate faulted transformers. Regular maintenance and testing of transformers and fuses can also help prevent failures and ensure the reliable operation of the power system. In summary, understanding the behavior of ungrounded Wye delta transformer banks under fault conditions is crucial for maintaining a safe and reliable electrical system. Proper protection and maintenance practices can help prevent equipment damage and ensure the continuous operation of critical loads. Let's further illustrate this with some concrete examples. Imagine a scenario where a factory utilizes a 13,800 volts/120/240 volts ungrounded Wye delta transformer bank to power its machinery. If a primary fuse blows but the corresponding transformer remains intact, the factory might experience a noticeable reduction in the performance of its equipment due to the reduced voltage on the secondary side. However, the equipment is unlikely to be damaged. On the other hand, if a fuse blows and the corresponding transformer fails, the factory could face significant problems. The voltage on one of the secondary phases would rise to approximately 208 volts, potentially damaging sensitive electronic equipment and causing motors to overheat and fail. This could lead to production downtime and costly repairs. Another example could involve a commercial building powered by an ungrounded Wye delta transformer bank. If a transformer failure occurs, the resulting voltage imbalance could disrupt the operation of lighting systems, HVAC equipment, and other critical building systems. This could lead to discomfort for occupants and potential safety hazards. In both of these examples, the importance of proper protection and maintenance is evident. By implementing appropriate protection devices and conducting regular inspections, it is possible to minimize the impact of transformer failures and ensure the reliable operation of electrical systems. It is also worth noting that the specific voltage rise and impact on equipment will depend on the characteristics of the transformer bank and the connected loads. However, the general principles discussed above will apply in most cases. Furthermore, the NEC National Electrical Code provides guidelines for the protection of transformers and electrical systems. Adhering to these guidelines can help ensure the safety and reliability of electrical installations. For example, NEC Article 450 covers the protection of transformers, including requirements for overcurrent protection and grounding. It's important to consult the latest edition of the NEC and local electrical codes for specific requirements in a particular jurisdiction. In addition to overcurrent protection, surge protection devices can also be used to protect transformers from voltage transients and surges, which can damage transformer windings and insulation. These devices divert excess voltage to ground, preventing it from reaching the transformer. Proper grounding of the transformer and the electrical system is also crucial for safety and to minimize the risk of electric shock. The NEC provides detailed requirements for grounding and bonding of electrical systems. When dealing with transformer failures, it is essential to follow proper safety procedures and to energize the equipment before attempting any repairs or replacements. Qualified electrical personnel should be involved in all work on transformers and electrical systems. Regular inspections of transformers should include checking for signs of overheating, oil leaks, and corrosion. Insulation resistance testing can also be performed to assess the condition of the transformer windings. By implementing a comprehensive maintenance program, it is possible to extend the life of transformers and prevent costly failures. In conclusion, understanding the potential consequences of fuse and transformer failures in ungrounded Wye delta transformer banks is crucial for maintaining a safe and reliable electrical system. Proper protection, maintenance, and adherence to electrical codes can help prevent equipment damage and ensure the continuous operation of critical loads. Remember, the increased voltage on a faulted secondary phase resulting from a transformer failure in this configuration can significantly impact connected equipment. Sensitive electronics and motors are particularly vulnerable. The unbalanced voltage situation created also poses risks. Therefore, proactive measures are absolutely necessary for system reliability and safety. It's worth reiterating some key aspects to keep in mind. Firstly, a blown fuse with an intact transformer leads to reduced secondary voltage, not increased voltage. Secondly, a blown fuse coupled with a failed transformer results in unbalanced secondary voltages, with a voltage increase of approximately 1.732 times the normal voltage and the faulted phase. Thirdly, the ungrounded Wye primary loses its neutral point reference when a transformer fails, causing the voltage shift. Fourthly, protection devices like overvoltage relays and fuses are essential. Fifthly, regular maintenance and inspections are vital for preventing failures. Sixthly, adhering to the NEC and local electrical codes is crucial for safety and compliance. Seventhly, qualified personnel should handle all transformer-related work. Eighthly, proper grounding and surge protection are important considerations. Ninthly, the specific impact of a transformer failure depends on the transformer and connected load characteristics. Tenthly, examples like factory, machinery, and commercial building systems highlight the real-world consequences of these failures. By grasping these key concepts and implementing appropriate measures, you can significantly enhance the reliability and safety of electrical systems utilizing ungrounded Wye delta transformer banks.